Okay, so last time we talked about the characteristics of the wireless signal in different frequency bands, and we said that in low frequency the wireless signal tends to penetrate through obstacles because the wavelength is very large, and if the wavelength, as a rule, if the wavelength is much larger than the body that it hits, then the wireless signal is able to penetrate through that object or that building or that obstacle. Whereas in the high frequency, the wireless signal tends to disperse or tends to reflect easily through obstacles, and hence we have some effect for some shadowing, and which we will talk about again today. And therefore, we have to, in very high frequency, like in close to light frequency, then we have to have line of sight in order to be able to communicate. Otherwise, we will not be able to communicate. We also talked about some characteristics of the antenna design. We discussed the isotropic antenna or the idealistic antenna, and then the dipole antenna and sectorized antenna, and how these different types of antenna, they use the special diversity or the special characteristics to be able to provide wireless communication. So today we'll continue this discussion and discuss the first the signal propagation ranges, and these signal propagation ranges are very important because they provide some bounds for us to be able to manage the wireless communication through different types of networks. So, for example, there is the transmission range, the detection range, and the interference range. In the transmission range, the transmission range is the closest to the wireless source. So when the wireless source emits the wireless signal, it goes idealistically, it goes through all directions equally, and it kind of evolves or travels through the air in like a spherical way, assuming that all the directions have the same kind of characteristics, assuming, like, for example, isotropic antenna, although of course it's not always the case. But idealistically, the transmission range is the closest to the wireless source, and it defines a certain range. Through that range, the wireless signal is detectable for sure. We can detect the wireless signal, and not only that, we can decode, and that's the most important thing. We can decode the wireless signal and get all the digital information out of it. So the wireless signal is considered to be like fully operational, and we can detect it, we can receive it successfully with high probability, so that the probability of loss in that range is low. Okay, which means that within that range there is low error rate, and the wireless signal can be received with high probability, and the signal can be decoded out of it. The detection range comes after that, and during that range, the wireless signal is detectable for sure. So you can detect the wireless signal, and by detection here, I mean you can distinguish the wireless signal from the noise. Okay, like you can see and you can sense that there is a wireless signal. Okay, but you can decode the digital information out of it with very low probability, which means that the probability of loss will be very high in that case. But the wireless signal is detectable. So if you get some antenna here in this range, in the detection range, in that case you will be able to receive some energy from the wireless signal. But this energy may not be enough to decode the information that's represented by this wireless signal. Difference is clear? Okay, clear? Okay.
Excuse me.
Okay.
It can receive some energy, and then, but might be not like.
Not enough to decode the signal, to decode the digital information. Okay, like we cannot. The wireless signal is required for what? We receive the wireless signal and then we convert it back into the digital domain to get the ones and zeros, which is the original data. So the wireless signal in that range will most likely be undetectable. Undecodable. Detectable but undecodable. Okay. Okay. So after that comes the interference range. In the interference range, the wireless signal is not detectable, but it acts as a background noise. So it's the level of power that you get here in the interference range is not even detectable. So you don't detect that this is an actual wireless signal, but it affects the transmission of other wireless signal that's in the same range. So it acts as a noise to other wireless communication sources. Okay? Clear? So the interference range is, so if I have an antenna here, definitely I will not detect that there is a wireless signal, and definitely I will not be able to decode anything out of it. However, if I'm trying to receive, for example, assume that there is another node here, okay, and this node acts as another source, and here I have the receiver for this node is here, okay. So definitely this node is in the transmission range of this node, right? Which means that this node will be able to receive and decode the signal from here. So in that case, this part acts as a noise to this transmission.
I'm not following that.
So this sender, when it sends the wireless signal, this node now is in the transmission range of this node, and it's in the interference range of this node, right? So most likely this node will be able to receive this signal with very high power, and it will be able to detect it. However, the reception quality will be affected slightly by the wireless signal from this sender. Slightly. So this will be the transmission, this will be the actual received signal, and this will be a background noise. Okay? The background noise affects the reception quality. And that's why here we're saying low error rate. We're not saying here no error rate. It's low error rate. Why? Because there may be some interference from other sources which affects the reception quality. Okay? Okay, clear? All right. So this is the communication ranges, and that leads to another topic here, which is very important: the signal propagation. As we have seen, the wireless signal travels through the air in a spherical way, idealistically, because we have discussed last time the antenna design and how it works and stuff. So idealistically, if we were to assume an ideal antenna, which is the isotropic antenna, the wireless signal will travel in a spherical way. So the actual received power on the surface of any sphere is proportional to the area of this sphere, which is the area of the sphere is 4 pi d square, where d is the distance or the radius of this sphere, okay. which clearly indicates that the received power decays by d square, which means that the power received is proportional to 1 over d square. Okay? Why? Because the actual power of the wireless signal, okay, when it travels through the air, the more distance you go, okay, the larger the sphere will be.
Right.
So the actual power that you receive on any surface is proportional to 1 over d squared. It turns out that this is actually in a vacuum. If we were to assume that we are traveling through a vacuum, which is not a practical case. A vacuum is an idealistic case. You don't even have air, remember. You don't even have air. Because air has particles, and particles affect the wireless signal. So, as a matter of fact, this d squared becomes something like alpha, where alpha we call it path loss exponent. And this alpha in a vacuum is 2. But in a typical wireless communication environment, it's like somewhere around 3 to 4. Or let's say like 2.7 to 4, something like that. So it's definitely above 2. Which means that the reception power gets affected by that. This is talking about a wireless source sending a wireless signal, okay, in normal environment, like in normal environment with air. We didn't start talking yet about if there is some obstacles here or there, okay. So the reception power is affected by the path loss exponent, which in a vacuum it's 2. This is the ideal case. But in a typical environment, it's even more than 2. Okay? Any questions? All right. So so this is the attenuation or the decay of the wireless signal, and we'll come to this later on when we try to discuss how when a node tries to receive from 2 different sources, what will be the best distance so that it receives from both nodes at the same time. And this is an optimization problem, but it's a simple one. So we'll discuss that, how the distance will affect that type of communication. So that represents or describes how the signal attenuates. So the attenuation is one of the major effects that happens to the wireless signal, which does not happen in wired, at least with the same level. In wired networks, the signal travels through the wire, so it does not decay with the same rate, for sure, right? Because it doesn't travel as a spherical, as a broadcast. It actually goes through a guided wire, so it doesn't decay with the same rate, for sure, right? And that's why in wires it's guided. They call it guided communication, and it actually can span longer range with a small amount of power. But in wireless, this is not the case. So another effect that happens to the wireless signal is what we call fading. So we have different types of that fading that includes what we call shadowing, reflection, refraction, scattering, and diffraction. So all these phenomena affect also the wireless signal, and it creates actually a major challenge for wireless communication. So shadowing. So remember again that we have the rule of thumb that if the frequency of the wireless signal is much less than the length of that obstacle, then we have high probability of what we call shadowing. Shadowing means what? Shadowing means that the wireless signal tends to not penetrate through the obstacle, and it gets affected by this. It gets blocked by the obstacle. It gets almost completely blocked. Okay, so the less the wavelength compared to the length of that object, the more shadowing will affect this wireless signal, in which case the signal is almost completely absorbed and nothing is reflected. Okay, depending again on the wavelength, sometimes the reflected power is significant. Okay, which means that if you are sending with a source here and you are receiving here, you may get actually a line of sight communication, and you may get the reflected signal as well. So you get both, which is, we will talk about in a minute, which is what we call multipath fading. Okay, so you get the line of sight and you get the reflected, because here, because of the characteristic of the wavelength of the signal compared to the length of the object, you may get some significant reflected power, in which case the reflected power is significant. Okay, so the only difference between shadowing and reflection is that in shadowing, the shadowing is like blocking. So the wireless signal tends to be absorbed almost completely into the obstacle, and nothing gets reflected. But reflection talks about the fact that the reflected power is actually significant, and we can use it positively for reception. Okay.
You told something about the lambda, the wavelength, no?
Right. So we said that this whole thing depends on the ratio between the wavelength of the signal compared to the length of the object. So if the wavelength of the signal is much less, the probability of shadowing and blocking becomes higher. Okay? So the less this wavelength compared to the length of the object, the more shadowing you will have. Which is evident when we talk about when we talk about high frequency signals. So that's why in high frequency signals, like when we go into the wavelength of light, the only way of communication is through line of sight, because any obstacle may actually block the signal completely. Right? Why? Because for light, the wavelength is really small. We're talking about micrometer in that case. So any obstacle, even a small rocket like this, if you put it, then it blocks the communication. Okay, so that happens specifically in high frequency ranges, but in medium frequency, like up to maybe 5 gigahertz or maybe 15 gigahertz or something, in that range, the wavelength is still like 1 meter or few centimeters or 50 centimeters or something. So in that range, not every kind of object may block. So you may get some reflected power as well, which means that you can have the effect of multipath fading. So we'll talk about that. Okay. So if you have two substances, if you have two substances, and there is a density difference, there is a difference in density. So similar to, if you remember the physics 101, so like air and water and something. So the wireless signal tends to act similar to light, more or less. So it actually refracts through the other substance. Okay, and the more the distance, the higher the distance of this substance from this, the more the wireless signal will be tilted.
The more the distance between.
The more the higher the difference between the density of this signal, the density of this substance, and the density of this substance, the more tilting will happen to the wireless signal. This phenomena is actually used to make sure that the wireless, because especially in low frequency signals, the signal can travel for a long range, right? We said that for low frequency signals, the signal penetrates and it goes for a long period of time, or it goes through a long propagation. And that's why we use that for submarine communication. We talked about that last time, right? So, especially when we talk about wireless signal, which travels for a long distance, someone might ask, if it's a too long of a distance, what happens to the surface of the Earth? Because the Earth is spherical. It's not a straight line. So when we say line of sight, okay, the line of sight in a small distance has some significance, but in a large distance, what about the surface of the Earth? And it turns out that actually the atmosphere has higher density in close to the ground, and the more the altitude above, the less the density will become, which helps the wireless signal stay close to the surface of the Earth, and that happens through the phenomena of refraction. Okay. Okay. So what happens if the wavelength of the wireless signal is very close to the length of the object? So in that case, the reflection effect becomes multiple, in which case we call it scattering. So again, if we talk about the range of the wavelength of the signal compared to the object range, here we're talking about if we were to assume that this ratio between the wavelength of the signal and the length of the object, if we assume that this ratio is alpha, okay, so here we're talking about alpha, which is much less than 1. Okay, right? So here we're talking about alpha, which is only less than 1, but not too much less. Okay, here we're talking about an alpha which is close to 1. Okay.
Just take my laptop.
All right. So when this happens, the effect of reflection becomes very significant, that the signal actually scatters. So you have more than one reflection. So we call it scattering in that case. That also happens if you have like a tip of a mountain like this. So also it actually refracts in multiple copies. Okay, so the same effect of scattering happens for refraction as well over a tip of a mountain or something like this. Okay, so the effect of these phenomena, whether shadowing, reflection, especially because shadowing is blocking, so it doesn't reflect much. So the reflected signal here becomes almost a noise. It's not detectable in many ways. Okay, but the effect of reflection and refraction and scattering and diffraction, all these causes the signal to propagate randomly, and you have no control what's gonna happen, and that creates the wireless channel dynamics. So just the fact that someone is passing by, he may actually cause some reflection and some diffraction and something like that, so he affects the wireless signal. They actually use this phenomena to, in some cases, improve the reception. Okay? So this is supposed to be channel impairments, but they try to twist this and use it in a positive way. Okay, so we have actually some applications that use the diffraction and shadowing and these effects to localize the person. So if someone is passing by, we know that there is some action in this room, so we can through some estimation and detection techniques and stuff, localize that there is a person in this room, and localize exactly where he is or where she is, okay? Because of the change of the characteristics of the wireless signal when this person is passing by. So that's one example of using this phenomena in a positive way. Another example, which is what we will talk about in a minute, which is multipath propagation. So multipath propagation talks about the fact that definitely when I send a wireless signal like this, again, I have no control. The wireless signal is going in this direction and this direction at the same time, right? So if the wireless signal goes in this direction, it does not reflect through any obstacle. But here, it reflects. So in that case, what I will receive is actually the composite of the two copies, okay? So that may affect the reception, but we will try to use that and twist it in and use it in a positive way to strengthen the wireless signal. If I use it carefully, then I can increase the reception power, not decrease it. Okay, so that's what we call multipath fading, multipath propagation. Okay, so so here, as we said, if the source is here and the destination is the car, so of course the source will send the wireless signal. So one copy of this wireless signal will go through the line of sight. There is no obstacle on the way, hopefully. So in that case, the signal will go straight without any obstacles. And there is another one which gets reflected, and there is another one which gets possibly scattered through that object. So you may actually get more than one copy here. Something like that. All right? In which case, what you will get essentially at the receiver is a copy of 3 paths. Okay? So if you were to send one pulse of a signal here, what you will actually get here is 3 copies of the same pulse. Okay? And it's deformed. And this pulse will become 3 copies here. And remember that due to the fact that the reflection will actually increase the path of propagation, as you can see here, there is a distance between the 3 copies of this pulse. And you may actually get some overlap, which is what we call inter-symbol interference. So you are trying to send 2 symbols. These symbols represent some digital information.
Okay.
We'll talk about how we use these symbols to represent digital information when we talk about digital modulation. That's a future topic. But here, we're trying to send 2 symbols, and what we get is actually, instead of the 2, we get 6 symbols here, and even some of them are overlapping. So that's a very challenging situation. Okay, so
But all of them representing the same data, the same signal, with different, let's say.
we call it multipath propagation, but we call this the difference between here and here. We call this something called delay spread. The delay spread is actually the difference between the first copy and the last copy that represents the same symbol.
So it's a copy, that's part of the path. So
It's a copy, a straight copy. And the more challenging condition now is that some of these copies may have less power.
Right.
Yeah. So that's a very challenging situation. Okay, so because of the fact that, again, the reflected power is not the same like the original power. So the copy that reflects through multiple objects will definitely have less amount of power compared to the one that went through line of sight. So that's a no-brainer. So the difference between the first copy and the very last copy of the same symbol, we call that delay spread. A delay spread is a function of the channel, of how the channel looks like. Typically, this delay spread is in the range of micro seconds. Like for example, in typical wireless LAN, the delay spread is around maybe 30 microseconds, something like that, not more than that. So the difference between the first copy and the last copy of the same symbol will be at maximum around 30 or 50 microseconds, not more than that. Okay, because this number affects the technique that we use on the receiver side to compensate for this. So there is a technique called equalization, channel equalization, at the receiver side, which tries to equalize all the copies to be the same, and also deals with inter-symbol interference to improve the reception quality. All right.
Inter-symbol interference and delay spread is the same.
No, the inter-symbol interference is the overlap between different copies. Okay. The delay spread is the difference between the first and the last copy that represent the same symbol. Okay.
What was the name again to equalize?
Hmm?
What was the name again to equalize the?
To equalize, it's called the equalizer, channel equalizer. They call it channel equalizer. We'll not get into the details of channel equalization, but it's enough to know that there is a technique called channel equalization that deals with this inter-symbol interference. Basically, it uses some specific filters to filter out, based on this delay spread, it tries to filter out these symbols and receive them with high quality and remove any overlapping between these symbols, which is what we call inter-symbol interference. You know the difference now? The difference between inter-symbol interference is that some of these copies that gets delayed, it gets delayed and overlap with the copy of another symbol.
Okay. Oh, that short period.
Yes, yes. In the middle, you get two symbols overlapping with each other.
Okay, okay.
All right. So this is called the inter-symbol interference effect. Okay. So for the effect of mobility, so far we didn't talk about mobility. So you can imagine. So first we talked about vacuum, and even in vacuum we have some effect in terms of propagation, wireless propagation. Then we talked about some obstacles. We didn't talk about the fact that the sender or the receiver are moving. So we get all these phenomena, given the fact that the sender and the receiver are not moving. So you can imagine if the senders and the receiver, sender and or the receiver is moving, then the amount of dynamics that you get in the system is really a lot. Okay. So if the sender and the receiver move, and or the receiver, if at least one of them they move, then the effect of multipath propagation becomes very dynamic, right? And it becomes really tricky for any equalizer to compensate for this, because the equalizer uses some kind of learning. So it learns that, okay, I have this delay spread, so I can use some filters here and filters there. So the channel does not change much. The channel itself does not change much, which is what we call here long-term fading. So the channel here, it changes, but it does not change much. Okay? But if the sender and the receiver are highly mobile, then it becomes really tricky for any equalizer to compensate for the inter-symbol interference efficiently. And you get the effect of what we call short-term fading. So the channel between the sender and the receiver changes a lot because of the fact that all the phenomena that we talked about, including shadowing and reflection, it happens dynamically because of the fact that the sender is moving. So the copies are different. The multipath propagation copies that you get are different. The delay spread will be different. It changes over time. which makes it really tricky for the equalizer to compensate for that. So you get the effect of what we call short-term fading, which dynamically, in a very short time, in a very short time frame, you get very low and very frequent changes of the channel due to the fact that it's actually moving. If the sender and the receiver are almost constant, then the effect of obstacles becomes in a way deterministic, and you get the effect of what we call long-term fading. So the channel does not change in a short term, changes on a long term only, but not in a short term. Okay?
Which is not the case. Usually.
Not always the case, because so in other words, it's evident to realize that wireless communication through mobility, through mobile nodes, is much more challenging. And that's why part of the standard of wireless communication, like in 3G, 4G, they specify the requirements in terms of the maximum data rate that you can send given certain speed. This is defined as part of the standard. For example, in 4G, you are required to provide maybe like 500 megabits per second in normal cases. But they say we can provide 500 megabits per second, and we can provide close to 100 megabits per second using a speed of up to 300 kilometers per hour. So they acknowledge the fact that when you move, you cannot send with the same rate. Definitely. Okay, because you get the effect of short-term fading, and the channel is really dynamic, and definitely the reception quality becomes really much worse. So you can send lower data rate in that case. But of course, there are some specific techniques to again compensate for mobility in highly mobile sender or receiver, and you can get reasonable data rates, but definitely not compared to the fact that when the sender and the receiver are fixed in the case of long-term feeding. All right, so so now we know that the propagation ranges, including transmission, detection, and interference ranges, and we know the different phenomena of propagation in terms of reflection, refraction, shadowing, and so on. And also we talked about the effect of multipath fading. So how do we manage wireless communication in such a way that we reduce these effects, the effect of interference, the effect of multiple nodes interfering with each other? We do that through what we call multiplexing. So multiplexing is the fact that you can provide multiple wireless communications, okay, using different characteristics of the wireless signal, including space, time, frequency, and code. Okay, so for example, space, we talked about that when we discussed sectorized antenna. We said that sectorized antenna is some type of directive antenna which directs the energy of the wireless signal towards a certain direction, okay, and neglects all the other directions. All right. So if we use directed antenna, which is it's close to the fact that we are trying to have a virtual wires between the sender and the receiver in a way, right? So in that case, you can have two different communications. So you can have one directed antenna here, which can have wireless communication here, another directed antenna here, which can communicate with another antenna here. Is there any interference between those two communications? In that case, no, right? Because here the energy is going into certain direction, and here the energy is going into different direction. So they are not interfering with each other. Okay, so in that case, we use the space, or they call it the spatial diversity. The spatial diversity, okay? So in that case, we divide the channel into different directions. We divide the channel is the environment around us. We divide it into space directions, okay? Time divides the channel into specific time slots, and frequency divides the channel into frequency time slots, and code does not divide the channel, but it uses certain codes which guarantees that even though you are sending the signal all together, but they are not interfering, which is a very interesting phenomenon, which we'll talk about. So the main goal of multiplexing is to facilitate multiple use of the shared medium. You have a wireless medium, which is basically the environment. For us, it's the environment. The environment being the surrounding, including the air and obstacles and everything. Okay, so we're trying to share this environment to facilitate multiple wireless communication that happens at the same time. How do we do this? So we have to use the four axes of the four different domains that we have, which is the space, time, frequency, and code. Okay? And the important thing here, which we will talk about, which the use of guard spaces. So when we divide the environment, either using space or using time or using frequency or using codes, we have to always keep some gap between these divisions, because the transmission or the wireless communication is not ideal. So when you allocate certain part of the channel, the communication inflates a little bit, and it gets overlapping with the other part. So in order to guarantee that they are separate, you have to keep some gaps in between. We'll see that. So the first thing, which is the most commonly used, which is the frequency multiplexing. So frequency multiplexing talks about the fact, remember that our axes now are the frequency, time, and code. Okay? And there is a fourth one, which we cannot represent in a 3D, which is the space. Right? So we know the space. We use the spatial directivity of the antenna to provide some space isolation between the different wireless communications. Frequency multiplexing talks about the fact that we separate the wireless communication using certain frequencies. So all the communication send at the same time, but at different frequency. So in that case, we can separate between them using what? So a node can receive any of these frequency bands using what? Using a simple filter at the receiver. It's like the radio. When we tune to a particular channel, what we are essentially doing is that we are moving the center frequency of the filter to filter out all these communications and leave only one channel to listen to. So in that case, a receiver may tune to a particular frequency range to be able to receive the signal in that range. Okay. The good thing about frequency multiplexing is that you don't have to coordinate these frequencies. For example, in a cellular network, we say that these three frequencies are used in this cell, these frequencies are used in this cell, these frequencies. So the nodes, they can use one of these frequencies to communicate, and you pre-configure everything and then you leave it. Okay? You don't have to do anything dynamically every now and then. So you just prefix these frequencies and that's it. You assign a certain frequency to a particular communication and that's it. So a channel gets a certain band of the spectrum for the whole time. So the advantages of this is that there is no dynamic coordination. I can prefix this from the beginning. I say, okay, so we can use 3 channels. Okay, if you want to receive this radio channel, then tune to this. If you want to receive the second channel, you tune to this, and so on. Everything is pre-configured, and that's it. I don't have to coordinate anything anymore. So it works only for analog signal, because what we are talking about here does not restrict the fact that this is digital or analog. So if we're talking about an analog signal, this works too, because analog signals, they have some frequency characteristics, and it's in the frequency domain they are continuous, and again using filters we can provide some analog communication. And in fact, amps, the first generation of wireless communication, uses some kind of frequency multiplexing. Okay, or in the case of hand cordless phones, or they call it walkie-talkie or something like this. So this uses some kind of analog communication. So you can tune to a different frequency and you can communicate. So there's no magic. I mean, it's very simple. The problem with that is that you have to pre-allocate this frequency for a particular wireless communication, even if there is no communication happening at the moment.
So it will reserve for nothing? It will be...
You have to reserve it because, again, you want to remove the coordination. You want to remove the controller that controls who will send in what band, right? So you don't have, you don't want to do this, okay? In frequency multiplexing, you don't have this centralized coordinator that says, you communicate on this frequency, no, everything is prefixed. Prefixing things is always bad in terms of utilization. Why? Because you may actually pre-allocate certain frequency range for a specific wireless communication, and nobody's using that frequency. For example, you are allocating a TV channel. For a TV channel, you are allocating certain frequency. So they decided to block the broadcast of that TV channel. So what's happening now? Well, the frequency range is still allocated, but it's never being used. It gets wasted. Okay. Whereas some other sources of, or some other applications, they require some communication, and there's no frequency range to pre-allocate to this type of communication. So that happens on a, so what coordinates this wireless communication is through regulation initially. So you allocate this frequency range initially through the regulation body, the regulatory body, and then it's fixed, even if you're not using it. That's it. خلاص. Okay. So if you're not using it, it's a total waste of time, which means that it's not flexible. It's not efficient in terms of utilization. Similarly, in a way, time multiplexing.
Yeah.
So instead of dividing the frequency, we divide the time. So in that case, we're not dividing the frequency. So you get assigned a time slot. You get assigned a time slot. When you get your turn, you can send using the entire frequency of the channel. The entire frequency is allocated to you, which means that you can send a very wide signal in terms of frequency, and you can send with high data rates, but in this time slot. in one particular time slot. Okay. Well, the advantage is here again. I mean, if everything is prefixed, again, you don't need any coordinator. Same thing, you don't need any coordinator. But again, the problem is utilization. But in addition to that, there is another phenomenon for the case of time. Okay? Because for time, you are trying to allocate a certain time for a particular wireless communication. For example, you have one node here. This is the source, and this is the destination. There is another source. This is source 1, destination 1. This is source 2. This is destination 2. When this source sends to this, it actually interferes with this. Right? So if this one sends, there is collision here, and the destination one will not be able to receive from both at the same time. Right? So we have to use some multiplexing. All right? If we use frequency, then we're fine. If we use time, which is our case now, then we will allow S1 to send a time slot. Let's say we divide the channel into time slot 1 and time slot 2, and you always have some gap in between. Okay? So this gap is important. All right? So at time slot 1, I will allow source 1 to send to destination 1. At time slot 2, I will allow source 2 to send to destination 2. So in that case, there's no interference. That's fine. But what's happening here is that S1 needs to really send during that time slot. Right? In order for S1 to know that it needs to send during that time slot, it needs to adjust its own clock. Right? To make sure that it sends only during this time duration and not before or after. Because if it's after, it will overlap with time slot 2, which means that it gets into the interference and we have the collision, right? So in that case, S1 and S2, they need to really adjust their clocks to make sure that they are in sync. They are in sync with the time slots that are prefixed. The problem with that is that you can never, almost never, okay, synchronize clocks of different devices. Our devices, so if you, my watch and your watch will have some time drift, no matter what you do.
Mm-hmm.
So in that case, there is some synchronization issue in that case. So if you leave the source and the destination to communicate for a long time, after a certain period of time, you get some clock drift, and the time slots may overlap. So you start having collision, and you get some issues. So, so the only way to make up for this is to increase the guard band. So increasing the guard band is one thing. And the other thing is that you try to use some synchronization mechanism between these two nodes together. You try to use some synchronization mechanism, and that's not straightforward, by the way. This is not straightforward. So in other words, S2, while it's not sending, it actually listens to the transmission from S1, not to receive anything,
Just
but to adjust its clock based on S1.
So
It's complicated. So you try to use some synchronization techniques to make sure that you always in sync with the beginning of each time slot. And it's not easy. This is dealing with the filters in the frequency domain for the case of frequency multiplexing is easier compared to multi-clock synchronization. Multi-clock synchronization is relatively speaking more complex. Okay. Any questions? So this is the advantage and disadvantage of time division multiplexing. So as you can imagine, we can combine the two and divide the channel into both frequency and time. So in which case, we divide the channel into what we call a resource block. A resource block is a specific time at specific frequency. GSM in second generation wireless, it uses this type of multiplexing where it uses a combination of TDMA with or TDM with FDM.
An
Okay.
example of TD time division alone.
Huh?
Example of time division alone.
Example of time division. I'm not aware of because for frequency first generation time division. Bluetooth is some kind of time division multiplexing. Bluetooth uses some kind of time division multiplexing, but Bluetooth also uses some. They call it frequency jumping, but it's a different issue. But the channel itself is divided in time. It uses TDM. GSM uses a combination of TDM with FDM. So it divides the channel into both frequency and time. But here, it actually requires some coordination. Why? Because I have to specify what resource block is used by which wireless communication. So when a wireless node comes into the range of a specific base station, we have the base station. We have the base station in the let's see. So we have here the base station, and we have nodes around the base station. Okay, so each one of these tries to talk to the base station. So the base station needs to coordinate which node uses which of these blocks to send to the base station. So we need some precise coordination to assign this resource block to each of these nodes to make sure that when two nodes are sending at the same time, they are sending at different frequency. If they are sending at different frequency, they use different time. Okay?
Same frequency.
Same frequency, so different time.
Yeah.
Same time, so different frequency.
Yeah.
So this whole thing has to be coordinated by a centralized coordinator, which typically is, for the case of GSM, it's the base station. The base station acts as the controller or the coordinator that assigns these resource blocks to the different wireless communication. Okay? Because of the dynamic, because here there is a point here which is better protection against tapping. What is tapping? Tapping here is listening to the wireless communication. Okay? So someone is trying to listen to the communication that is happening between any source and destination. So you have like a node, eavesdropper. For security, you have like eavesdropper who is actually listening to the channel. As you can imagine, for the case of FDM and TDM, everything is prefixed. So any tapper or eavesdropper will be able to listen to that with no problem, right? Nothing is changing. The frequency is not changing, so he or she can tune to a particular frequency and listen to the communication. For the time, I know that, if I want to listen to a specific node, then I tune myself to a specific time and I read what this node is sending, because everything is fixed. Here, I have some kind of protection against this tapping. Why? Because every time I may actually change the time or the frequency. Okay? So the fact that this provides some dynamic way to assign the frequency and time makes it more resistive to tapping. Okay? So the fact that I can assign these time slots and frequency ranges dynamically and change it from time to time makes it a little bit hard for someone to tap into the channel and listen to what I'm trying to send. So if he listens to that frequency at this point in time, chances are in the next like 10 seconds, I will use another frequency range. And he doesn't know that. The only one who knows that is the coordinator. But the tapper or the eavesdropper doesn't know that. So at least I get some protection against tapping. Okay? The other thing is protection against frequency selective interference. What does that mean? There's a problem in FDM. That if you pre-allocate certain frequency bands to a specific wireless communication, that's not only inefficient in terms of utilization, but it's extremely unfair. Why? Because the different frequency ranges will not have equal level of interference. Right? Because some frequency range may have, multiple nodes interfering with it. Another frequency range may not have the same level of, or the same traffic jam in terms of, so for example, I tune to a particular channel. This channel happens to be the same channel that's used by the microwave. So the microwave will interfere with me. But another channel, maybe it's not similar to the microwave, or it's not similar to this radio station, or something like this. So the interference in every frequency band is not the same. Okay? So they call it frequency selective interference. Frequency selective interference. So the interference across the different frequency ranges is not balanced. So typically, it's not balanced. It's not equal. So when I come and say, okay, I will pre-allocate these frequency ranges to particular wireless communication, what I essentially did is that I favored some communication over the other. Right? Because some communications will have less interference, some communications will have more interference. Right? So in that case, it's not completely fair. Okay, so I allocate certain frequency band, and it happens that this frequency band is really crowded, and it has high level of interference. For this, because of the fact that you change the frequency from time to time, okay, so if you are favored this time, chances are in the future you will be degraded and someone else will be favored. So this dynamic kind of assignment creates some fairness over time. Because if I'm favored at this time, later on, I will be degraded. And if I'm degraded at this point in time, I should not be sad, because in the future, I will get another frequency range, I will get another time slot, and in that case, I may have better performance than the others. So if we are jumping between frequency and time, chances are, over time, it will be fair. And of course, we have to also make sure that the number of resource blocks assigned to a particular nodes are balanced in a way. Of course, we didn't talk here about service differentiation and stuff like that, which is another topic altogether. But balance doesn't mean equal. Balance doesn't mean equal. It's sort of being equal or providing equality, like like equality, like even between women and men, does not necessarily mean that you have the same rights. No, I give you different share, but actually using this share, you will be more balanced overall, because of the fact that your demands and your requirements are different. So I'm giving you some provisioning, okay, to fill the gap of what you demand. So in that case, overall, I will be fair. Okay? So fair does not necessarily mean I give you the same thing. Okay?
You mean balance is not equal?
Balance is not necessarily equal, yes. So I should be balanced, but not equal. I should be fair, but not equal. Okay? All right, but so the main issue here is the coordination. But other than this dynamic assignment gives us protection against tapping or eavesdropping, gives us protection against frequency selective interference. All right, which is a good advantage. Okay. All right. So, of course, we talked about frequency. We talked about time. We talked about frequency and time combined. All right. The remaining part is to talk about code. All right. So before that, we need to talk a little bit about cognitive radio, because the fact that we can assign the channel in time and frequency in a dynamic way, okay, leads to the fact that we can have a smart spectrum. Smart spectrum means that if we were to draw a map, okay, of the frequency and time ranges that are consumed at any point in time, it would be perfect to draw this map, because then we will have some gaps here. So this is a gap, and there is a gap here, and there is a gap here, and there is a gap here. Okay, so these are like some, let's say, like this is a TV channel. All right, but this channel is not broadcasting at this point in time. At this point in time, maybe in the future it will. Okay. That's maybe a Wi-Fi, which is currently the access point is down. Okay, and this is basically maybe ad hoc communication, and ad hoc nodes are not in the range at the moment, and there is no communication. All right, so it would be perfect if we can draw a map of what are the communications that are using a specific range of frequency and a specific range of time at any point in time. Because if I know this, I know where the gaps are. Okay? And I can try to fill these gaps using what we call here secondary users. These are This is what we call secondary users. So cognitive radio here talks about a smart spectrum utilization. Because we know that these primary users, these are users who paid money to communicate wirelessly in this range, right? So they paid money. I cannot tell them stop because another person or another wireless communication whom they did not pay anything and they want to communicate, all right? So just the fact that they paid money, it doesn't mean that they are utilizing this spectrum or this time 100%, right? The fact of the matter is they did some measurements in the US, like in many countries, and they found that at any point in time, close to maybe 80% of the spectrum is not used on average. So these people, they have paid money, but paying money does not mean that they are utilizing the spectrum 24/7. So they came up with the paradigm of cognitive radio. Cognitive radio is like smart spectrum utilization. So not only do we have a coordinator that coordinates the frequency and time, but this coordinator also senses which part is not used at any point in time. And if any of these gaps are there, then they allow what they call secondary users. Secondary users are users who did not pay anything. Okay? But if nobody's using this spectrum,
They will give them the chance.
they will
to
give
use
them
it.
the chance to use that spectrum at this point in time. Once the primary user comes into the picture, he will take precedence, and the secondary user will have to abstain from transmission. This concept, it looks novel, but in terms of implementation, it's really hard. It's really hard because remember we talked about detection range. This requires a very sophisticated hardware to be able to sense in real time who is sending at any point in time at any frequency range. So a very important component of cognitive radio is what we call sensing, cognitive sensing. All right? When it declares that certain gap of frequency or time are not utilized, then it declares that this part is usable by secondary users. Okay? So these secondary users, they have to coordinate with some base stations, and then the base stations will allow them to send or not to send, even though they didn't pay anything. Okay? So cognitive radio talks about the fact that there are primary users, and these users are licensed users, they paid money to access, and secondary users whom they have to be very smart. They need to sense and make sure that the spectrum is not used at any point in time, and then use that spectrum for a particular duration, and then goes out of the picture to allow the primary user to. And of course, this cannot be ideal. So the secondary user may, in fact, because the probability of detection is not 100%. So you may actually declare that there is a spectrum that's not utilized, even though there is a chance that it's utilized. Right? So it's a false positive. In which case you try to use the spectrum, you affect the performance of the primary user negatively. All these issues are part of cognitive radio. So they try, if there is a chance to have false positives, then cognitive radio tries to reduce that probability to close to zero, to try to make the communication successful. In some cases, they even derived models, and we have so many publications about this, that the secondary user will act as a helper to the primary user to allow the primary user to finish transmitting its own traffic quickly. Okay? If that happens, that the primary user will finish communication and will get out of the way. So it allows you to use the spectrum. So similar to, like, remember, like replay attack. So it's not an attack in this case. The primary user cannot reach to the primary destination because of the long range. Okay, which makes the probability of successful transmission low. So the secondary user comes into the picture, increases the probability of successful transmission by helping the primary user. If I help the primary user will finish faster, right? If he finishes faster, he gets out of the way and he gives me the chance to. So it's like a win-win situation. That's also part of cognitive radio. They call it cognitive relay. So the paradigm of cognitive radio here is really huge, and there is so much work related to that. And until today, there's a huge amount of research in that direction. All right, and it talks about dealing with the spectrum as a smart resource, and I can use this smartness to increase the utilization of that spectrum. Okay. All right. So. All right, so the fact that the spectrum has become really smart allows the secondary user now to be able to send using any frequency at any point in time. Right? The secondary user.
Yes, if there is. Okay.
Because the primary user is designed to use that spectrum. Mm-hmm. It's a device which is designed to use that spectrum, right? Mm-hmm. But the secondary user is some kind of a عارف متسلق he's trying to be opportunistic, right? He's trying to find any gap and then gets in to use it. Mm-hmm. Okay? Mm-hmm. So in that case, I cannot use a specific designed hardware for a particular frequency range because I don't know which frequency range I'm going to use. I don't know which time I'm going to use. Okay? So this actually evolves to using the concept of software-defined radio. What does that mean is, typically, the physical layer is designed using hardware, pure hardware, right? Hardware which is composed of digital circuit for baseband and analog circuit for RF. Okay? But it's hardware, very sophisticated hardware. And this hardware is designed with some specifications to support certain frequency range, certain synchronization, designed based on specific delay spread, and there is certain parameters based on which I designed this hardware. So it's not reconfigurable easily. Okay? But the concept of smart spectrum dictates the fact that we cannot use a pre-designed hardware which is optimized for a specific frequency range. We have to use ultimate flexibility. And ultimate flexibility is always provided using software, not hardware. Okay? So there is also now the paradigm of software-defined radio. Software-defined radio talks about the fact that the baseband, including modulation, including quantization, all of this is done using software, not hardware. So the hardware that we use is only digital to analog or analog to digital converter. That's it.
Okay.
All the other techniques, including quantization, modulation, coding, dealing with multipath propagation, dealing with all of this, is done using software. So in that case, I can be very flexible, extremely flexible. I can change the radio to use certain bands. Okay? Using this concept, I can technically tell you, okay, I can upload certain software on your mobile, and your mobile now is 5G enabled. Can we do that nowadays? Can we do that nowadays?
5G.
Can we support 5G on the cell phone, on the same cell phone that I have now?
Currently?
Currently, no, we cannot. Why?
It's designed for LTE only.
It's because the hardware of this mobile
Does
phone
not support 5G.
does not work with 5G.
Mm.
The whole hardware is designed based on certain parameters and certain regulations and stuff, which supports only 4G or supports only 3G. Okay? So if I want to switch to 5G, I have to change the hardware. Using this concept, I can send you a patch software, and all of a sudden your device will be 5G enabled, 6G enabled, something like that. Which makes the cell phone extremely flexible and very smart and highly reconfigurable. But of course, this is again is very hard. It's not easy. Software-defined radio has started maybe around 5 years ago, and it won't be before at least 20 more years to become really commercially viable. But the fact that you have now very sophisticated hardware, which is in terms of running complicated software like this, it will be fast. Because the problem with software-defined radio is always the speed. Because the speed of software is nothing compared to the speed of hardware. So the good thing about software is flexibility. But this comes with a cost. Running complicated software will take longer time. And that's why we need hardware, right? So this is the problem now. So software-defined radio, it gives us the flexibility, but it comes with a cost. That speed will be low. So I'm not aware of any software-defined radio which supports high data rates at the moment. Anything close to the normal hardware. But this concept has been triggered by cognitive rate. Cognitive rate is all about smartness, is all about being flexible, being able to reconfigure yourself based on what's happening around you. So that requires ultimately flexible and reconfigurable type of blocks, and that can be implemented using software, which we can understand, but this comes with a cost which is low speed, at least at the moment. Maybe in the future it will be able to provide higher speed. So I had a master student who worked on software-defined radio a while back, maybe like 3 years back. And I remember we were talking about like 1 or 2 megabits per second, not more than that. So he used actual hardware which runs all the radio. He actually implemented radio using software, like code, normal code, using Python.
Okay.
So using Python, you can design an equalizer. You can design a channel coding technique. You can design a modulation technique using software, using normal code. Okay, but the problem is that when we try to increase the speed, everything fall apart. So it doesn't work. So as long as you are low speed, you can, because synchronization and all these issues, it takes time. And synchronization will not allow you to run a code for a long time and to compensate for the clock drift. Of course, there will be some missynchronization in that case. So as long as the speed is reasonably low, you can get by using software-defined radio. But definitely, this gives you ultimate smartness. So he was able to use 2 devices and change channel and be able to maneuver across the spectrum and provide some communication depending on sensing the environment, and that was really impressive. So there is the most common framework which is used for software-defined radio is what we call GNU Radio. GNU Radio is open source. It's open source code which represents all techniques of physical layer. Okay, it's implemented using C++, and what you need to do is to write like a Python code over this kernel of C++ to configure your radio. So you write a Python code that access the kernel to let the kernel know what frequency band you will use at any point in time, what time slot, whether to do sensing or not, and so on and so forth. How to do synchronization, how to do equalization, how to do this and that. So it's like you have blocks implemented in a kernel, and using the Python you can select from these blocks and you can reconfigure your software in any way you see appropriate. So you can change the radio at any point in time using purely software. Your hardware is basically digital to analog and analog to digital. That's it. So you connect the digital to analog to the antenna to send wireless signal, and then when the wireless signal comes back, you change from digital to analog and then continue the reception. And then all this is software.
Mm-hmm. Doctor, when you are talking about speed, you mean processing speed? Or
Yes, processing speed. Because right now in 4G and 5G, and you can get high data rates, but that uses hardware, so very sophisticated hardware. And this hardware is optimized to give you that speed. But the cost that you have to pay is that it's fixed radio. All the parameters of this radio are predefined. You define it based on the standard. So you know what you are implementing exactly. The problem with cognitive radio is that I'm not following a specific standard at the moment. I can change the frequency, I can change the time, I can deal with different type of equalization based on the current environment.
But if we are talking about mobility, then the environment will change like regularly, right? So speed is important.
Of course, speed is important from the multipath fading point of view and all the phenomena that we talked about. But you can be mobile but use the same frequency and the same time. Like you have a certain, so when you connect to a particular base station, Okay?
Okay.
The base station will tell you what time to send, and the frequency you are designed to use specific set of frequencies, not more than that. Like three frequency bands. That's it. So your hardware and everything is optimized based on this. So when you move,
Another
your
antenna.
equalizer will compensate for multipath fading and intersymbol interference, and this is also hardware. So everything is designed based on the fact that there are some characteristics that are specified in the standards, and you design your hardware which is optimized for this set of specifications. Cognitive radio here comes with ultimate flexibility. I may be actually using a TV band at the moment. Later on, I can use 2.4 gigahertz that's used by Wi-Fi. And I should be opportunistic and be able to. So, of course, you can use cognitive radio without software-defined radio. That's also possible. You don't have to use software-defined radio to be able to implement cognitive radio. So you can use cognitive radio using specific hardware, but you will be limited in terms of frequency bands that you can support, right? And you will be limited in terms of reconfigurability when the environment changes, right? But you will still be dynamic in terms of assigning the frequency bands. But in that case, the maximum you could use maybe like 10 channels, okay? Something like that, but not unlimited. But software-defined radio gives you the ability to be able to have ultimate flexibility and to change your radio at any point in time using the code, which is the ultimate flexibility. But of course, it comes with a cost. At the moment, it's just now it's just a concept. Until today, and I don't think in the next 10 years it will be commercialized, because currently the speeds that we're talking about is really low. But currently they use software-defined radio for education and stuff to demonstrate to the students how we can reconfigure the radio. It's really nice in terms of you see the code, how you design the equalizer and stuff, and then you design your equalizer, you design your channel coding, you design your modulation, and then you see it running. You see actually an actual signal going, but this whole thing works in low speed, okay, not in high speed, okay. All right. So the last thing here is code multiplexing. So we talked about frequency, we talked about time. The best way to get the feel of code multiplexing is to imagine that you are in a meeting. Okay. So currently we are the four of us, or maybe some other people are sitting in the same room. All right. So we can use space to communicate. I can communicate to you in a private way, which does not affect the communication that's happening now. So as long as I use specific power and I direct my communication only to you, we will not interfere with the communication that is happening on the others. In that case, we're using some kind of space multiplexing, right? Or you can, the same thing can be frequency. Or I can be in a meeting and say, I'm the moderator, and I'll give you the turn to talk now. When you finish, I will give you the turn to talk now. So what we are essentially doing is TDM, right? So we are dividing, so we can. So when I give you the opportunity to talk, you have the entire channel available for you. You can use it for a certain period of time. You can use high power, you can increase your rate, you can do whatever during this time. You are free to do whatever you want during this time, right? So otherwise, if we don't do this, and we are talking like this, and we are talking the same language, and there is another communication happening here, so imagine that you two are talking and we are talking, okay, in a similar power, more or less. So you will not be able to recognize what I'm saying clearly, right? Because you have some interference from the other communication, okay? Code multiplexing comes into this picture and say, that's not necessarily true. So imagine if we are talking using Arabic language, and they are talking Chinese, okay? So imagine yourself that you currently, you are receiving two communication at the same time, at the same frequency. But they are extremely two different languages. Extremely two different languages. Will you be able to distinguish one from the other? The answer is yes. In many cases, yes. Right? So, codes are some like specific digital information which codes the traffic that I'm trying to send in such a way that makes the communication, even though it's happening at the same time, but they are, we call them orthogonal. Orthogonal. That if you try to get the correlation between the two communications, you will find that the correlation is null, is zero. Okay? So if I give you the code for the Arabic language, okay, you will tune your brain to listening to Arabic language and you will be able to decode what I'm saying. If you change your code to Chinese, which means that your brain now understands Chinese, even though I'm talking to you in Arabic, you will be able to decode what they are communicating at the moment, more than the Arabic. So that's what code multiplexing, that's how it works. So before we send the traffic, we use a particular code and we multiply this code by the data to give it a particular, let's say, language. That this language makes it too far from another communication, which uses another code. So the condition to be able to do this is that the two codes that are used for the two different languages, we call them orthogonal to each other. Okay? Orthogonal means that if you try to get the product of the two codes, the product of the two codes is always zero. Which means they are not correlated. They have no relation with each other. Okay? But when you multiply the code by itself, you get really high correlation. Your correlation in that case will be the decoded signal that I'm communicating to you. Okay? So to be able to do that, you have to first, from the source point of view, you have to get the code multiplied by the signal, multiplied by the digital information that I'm trying to send, and then send everything at the same time, at the same frequency. And in the air, they will mix, but you can use a specific code to get one from the other. How? Because this code, when it gets multiplied by the other code, the correlation will be zero, which will nullify this communication and will get you only my communication. So in that case, it's clear that this is very bandwidth efficient because I can allow two communications to happen at the same time, at the same frequency, which is really good, right? But it doesn't come for free. Definitely, it doesn't come for free. So there is some cost that you have to pay. Still, the coordination here is low. The coordination is low,
Right.
which means that you pre-assign the codes. So you have the code to Arabic, so you will be able to listen to what I'm saying, not what they are saying. Okay, you have the code for Urdu, so she will be able to understand this language. Okay. Also, there's no need for synchronization. There's no time aspect in here. There's no time aspect in here. So we can talk at any point in time, right? Because we don't have to synchronize any time slots, right? So there's no synchronization needed. there's still some good protection against interference and tapping. Why? Because unless you know that code,
You won't be able to.
you won't be able to decode anything. Okay? So we have to synchronize that you have the same code I'm using. If you're not using the same code, you'll not be able to listen to what I'm saying. So you have some level of protection. Again, this level of protection becomes loose if these codes are pre-assigned. If these codes are pre-assigned, sooner or later I will get the code, I will be able to decode. Right? But if you are changing these codes once in a while, then you get better protection. All right. So this is the advantage. So the advantages is that, of course, it's bandwidth efficient because I'm sending at the same time, at the same frequency. There's no coordination. There's no synchronization. And here by synchronization, I mean there's no synchronization between time slots because we didn't talk about any time slots here. And there's good protection against interference and tapping. That's, again, if these codes are not pre-assigned. Yes. So the disadvantage here is that synchronization is needed. And someone might ask, we say no synchronization needed, but synchronization is needed. So this is a little bit misleading. What this means is that the synchronization for the traffic itself is not needed, but the synchronization for the codes is needed. Because these codes, the code is actually, we can think of a code as a vector of a binary. We can think of the code as a vector of binary ones and zeros. So this is a code. So that's a typical code. This is a code. Okay? And another code could be 01, 00, 1, 0, 1, 0, 0, 0. So these codes are orthogonal. How did I know that?
XORing.
Yeah, so XORing all of them, the answer will be 0. So first, I will have to get from source 1, I get source 1, multiply it by this code, and then send the result. Source 2, multiplied by this code, send the result. So when I send the result at the same time, at the same frequency, those two will mix. Right? They will mix, but I will still be able to distinguish one from the other. So at the receiver side, if and only if I have this actual code, I will be able to decode, right? So the thing is, this code gets generated at the sender and gets generated at the receiver.
Okay, right.
So only if I generate this code in a synchronized way between the sender and the receiver, okay, if there is a shift, so essentially there is a 1 bit of shift between this code at the sender and this code at the receiver. So I will not get the high correlation that I'm talking about. Because remember, when you get this composite signal, if you multiply by the same code, you get very high correlation. Right? If you multiply by any other code, you get 0. Right? If there is a shift, I will not get 0, but I will not get the maximum correlation. I get somewhere in between. So the reception is good when there is a synchronization between the code at the sender side and at the receiver side. So here, the synchronization that we're talking about is required for the code, not for the traffic itself. For the code, not for the traffic. So here, the synchronization is for the code, for code generation. Okay? So of course, as you can imagine, the signal regeneration requires some higher level of complexity because I have to multiply the code by the signal, which regenerates another signal, which is the coded signal. I didn't have to do that for FDM and TDM, right? Right? For FDM and TDM, I didn't have to do that. I send the actual data as is. I don't do anything, right? But here, I have to multiply the data with the code, which is also some added complexity that I have to do. Okay? So, what is the concept of near-far effect? The concept of near-far effect is a specific phenomenon which tells you that you can get, well, when you get a composite signal, you can get high correlation with the node, with a specific signal, and you nullify the other signals, only when the level of power of both arrives to the receiver at the same state. If there is one uses very high power and the other one uses low power, then this high correlation may not work perfectly, because you have imbalance in terms of the one signal arrives with very high power and one signal arrives with very low power. If you want to understand this, again, we apply it back on our example. If I'm talking to you in Arabic and they are talking in Chinese, if we are talking in the same level of voice, you will be able to understand the Arabic and be able to distinguish it from Chinese. Imagine if I lowered my voice and they raised their voice very high. Okay? So in that case, even though you understand Arabic, but Arabic will be in the level of a noise to you, and Chinese will be the dominating signal. So in that case, you will not be able to distinguish, right? So this is the near-far effect. So in order to guarantee the high correlation when I receive a particular signal, both signals need to arrive at the receiver with the same level of power, which is a very tricky situation now. Why? Because as a receiver, I cannot control where the sender is, because we said that the wireless signal attenuates based on the distance. So as a receiver, my distance to different senders is different, right? So inherently and intrinsically, I receive two signals. If they use fixed power at the sender, the received power will be different, right? صح? The received power will be different, right? So we will have the near-far effect. So the only way to compensate for the near-far effect is by adjusting the power at the sender. So by adjusting the transmission power at the sender. So near-far effect, and this is again another cost that I have to pay for code division multiplexing. So code division multiplexing has to come with an adaptive transmission power. Why? Because I need to have equal power at the receiver. I need to have equal power at the receiver. So the only way to have equal power at the receiver is to change it from the sender, because the distance between the receiver and the sender is different, right? So in order for the receiver to be able to have good reception quality, the different senders need to adapt the power relatively to have near equal power at the receiver, in which case the receiver will be able to distinguish any signal from the other, assuming that it uses the right code. So here, the near-far effect is another disadvantage for the code division multiplex. So these two are major, especially the synchronization for the generated signal, for the generated code, is really not straightforward. And again, it's always synchronizing a clock between two different nodes is not easy. Of course, it's solvable, but it requires some complexity. And the other thing is, again, near-far effect. How can I compensate for the power to arrive to the receiver at the same level? That's another issue that we have to deal with for the code division multiplexing, which otherwise we did not have to deal with for the case of frequency, and for the case of time, division multiplexing, and for the space. So the codes are generated using the concept of what we call spread spectrum technology. So we'll talk about this later, how we make sure that these codes are orthogonal, and how do we generate these codes. There is a specific rule by which we can generate these codes and be able to communicate. Okay? All right, stop here. We'll talk about digital modulation next time. So.